All right, objective 3, we want to solve our right triangles. To solve a right triangle means to find the lengths of its sides, which our sides are going to be rounded to 2 decimal places if necessary, and the measurements of its angles rounded to 1 decimal in degrees. We're mostly going to be working in degrees, but occasionally you may see radians. So if we do have degrees, remember we want to round that to 1 decimal. So in all, solving a right triangle just means that you're finding the lengths of the sides and the measurements of the angles. In order to actually solve a right triangle, you need to know one of the acute angles, so A or B, since we already know that we have a right angle in there too, which is 90 degrees. So we'll need one more angle and a side. So the combination there, we need another angle and a side, or we just need 2 sides. So in our triangle labeled here, we see we have our triangle, we have our 90-degree angle in our hypotenuse, we have our side length A and our angle A, and then we have our angle B and our side length B. So then for properties of a right triangle, from the triangle, or the right triangle showed in our figure, which is corresponding to figure 7 in the book, we now have that c squared is equal to a squared plus b squared, and a plus b is equal to 90. So now that we have our right triangle, these are our properties. These are always going to be true when we have our right triangle. All right, so example 3. We want to use the picture below to find the values of A, C, and capital B if lowercase b is equal to 2 and capital A is equal to 35 degrees. So all these things are labeled in our triangle here. We see we have our right triangle, our 35 degrees, which is capital A, corresponds to our lowercase a. Then we have our lowercase b is equal to 2, which corresponds to our uppercase angle B. And then lastly, we know here that we have our 90-degree angle, which corresponds to our hypotenuse. So, all right. So we can state that since A is equal to 35 degrees, and we know that A plus B is equal to 90 degrees, we can get that B is going to be equal to 90 degrees minus A, which is 90 minus 35 degrees, which is then going to be equal to 55 degrees. So B is equal to 55 degrees. Let's write that down. B equal 55 degrees. So now we know our angle B. Now we want to find the lengths of sides A and C. So to find the lengths of A and C, we can use the fact that we know tangent of 30 degrees, or sorry, tangent of theta. I was thinking theta and then a degree measurement. So tangent of theta is going to be equal to side A divided by side B. So the angle that we want to think about here is going to be, let's say, tangent of 35 degrees. If we pick tangent of 35 degrees, this means that our opposite value is A, so this is opposite, and our adjacent value is 2. So tangent of 35 degrees, we're going to state that this is going to be equal to A over 2. Now, if we want to find the lengths of C, We're going to go ahead and erase that. And if we want to find C, we can use the values that we already know, which is 2, which if we still want to use 35 degrees, this means that we're going to use our adjacent over our hypotenuse. And we know that adjacent over hypotenuse is going to be cosine. So we can find the value of C by stating cosine of 35 degrees, that angle measurement that we chose there, is going to be equal to adjacent over hypotenuse, so 2 over C. And now we can go ahead and rewrite these so we see simplified down what they end up being. So we can rewrite this as now A is equal to 2 times tangent of 35 degrees. And now C is going to be equal to 2 over cosine of 35 degrees. And at this point, we need to use a calculator. If you do end up with really nice degree values that are easily found in the unit circle, you can go ahead and just calculate those using the unit circle, or if you can memorize those values, go ahead and do that. But a lot of the times with these problems, we're not going to get those nice, pretty values. So we are going to have to use our calculator a lot in these sections. So for A is equal to 2 tangent of 35 degrees, we want to plug this into a calculator and round to 2 decimal places. And when we do that, we end up with the value of about 1.40. Then for C, or for length C, if we plug in 2 divided by cosine of 35 degrees, this is going to give us a value of about 2.44. And that there gives us the values of capital B, lowercase a, and lowercase c. So let's write just our final answer here. And say thus, we get that our angle B is 55 degrees, our length A is 1.40, whether to include the 0 or not, it's up to you. And the length C is equal to 2.44. So, all right, so it was fairly easy since we were given the values of 2 angles and 1 side measurement. So we were able to find that last angle, and then we were able to find 2 other side measurements using our trigonometric function for triangles, right triangles specifically. So all right, objective 4, we're going to solve applied problems. So we can use right triangle trigonometry to measure heights and distances that are either awkward or impossible to measure by ordinary means. Vertical heights can be measured using either the angle of elevation or the angle of depression by measuring the acute angle from the horizontal to the line of sight of an object. So something like this. So using our angle of elevation or angle of depression, this would give us the value of maybe how far away we are from something or the height of an object coming from our line of sight. So for an angle elevation, we're going to say this is our eye here. So that's our eye. It's not very pretty, but so this is our eye. So this is our sight. So we have our horizontal length going away from this object, which in this case is a dog. So we're looking at a dog here. So we see we have this horizontal distance, so how far away the dog actually is, and then how high up the dog actually is. And when we look at it, we're looking at it with a straight line, which then becomes our hypotenuse. and the angle from the ground, or whatever our horizontal is, with the angle of how high we're looking up, that gives us that angle theta. So with an angle of elevation, it's going to be some sort of, here's the ground and you're looking up, and that's how you use your angle of elevation. Very similarly with your angle of depression, if you are using your line of sight here, so if this is your eye, sure. So this is your eye, your line of sight, you have your horizontal, so in this case, we're working with a cat, so how far away our cat is, and then how far down our cat is. So that length downwards is going to be where our cat is. So when we look at it, we're looking down, and this line of sight here is going to become our hypotenuse, and then the angle at which, if we were looking straight, but now we're looking down, this angle here is now going to be the angle that we're using in our angle of depression. So this would be the angle that we would use in order to find the values. So this being the angle that we would use in order to find opposite, adjacent values of hypotenuse, and also your angles. So let's go ahead and do an example of this. So this is copied from the book, so if you would like to look at it any time, this is in your book, as well as many other examples of using applied problems with right triangles. So example 4, we have that meteorologists find the height of a cloud using an instrument called a ceilometer. A ceilometer consists of a light projector that directs a vertical light beam up to the cloud base, and a light detector that scans the cloud to detect the light beam. So see the figure 13a. So 13a is our actual illustrated image here. We're seeing that at Midway Airport in Chicago, a ceilometer was employed to find the height of the cloud cover. So we see we have some clouds here at the top, and it was set up with the light detector 300 feet from its light projector. So we have our light projector, so we have this essentially a lamp that is shining light up to the cloud cover, and then we have our light detector that is sitting about 300 feet away from it. So if the angle of elevation from the light detector to the base of the cloud was 75 degrees, what's going to be the height of the cloud cover? So we go ahead and fill in these values. Let's zoom in here a little bit. We see that base B is 300 feet, and our angle here is 75 degrees. What we can also notice is that this is a right triangle. So we know that this is 90 degrees. And in figure 13b here, we do actually see what's written out. And we're looking for the height. So in figure B, this is just a simplification of the image that we actually have drawn out in figure 13a. So we see we have a right triangle. Our base here is 300 feet. We have our height, and our angle here is 75 degrees. And we want to find the height. So we're thinking about the height. What we already have is we already have this adjacent value. And what we want is the opposite value. Because we see here that this length here, that's our hypotenuse. That is the one that's going diagonal. The height we're looking for is our completely vertical line. So what we're looking for is we want to use something that uses opposite and adjacent. So we could say we have the angle measurement, the adjacent side, and we want the opposite side. Now the trigonometric functions that include opposite and adjacent are going to be tangent and cotangent. And since we use tangent more often, it's in kind of our base 3 within our 6, let's go ahead and use tangent. So if we want to use tangent, so we'll say here, use tangent. If we're going to use tangent, we know that according to our definition, that we get tangent of theta, which in our case is going to be 75 degrees. We say that tangent of 75 degrees is equal to opposite over adjacent. Yeah, it is opposite over adjacent. So this is going to end up being h over 300, or height over 300. So then if we want to solve this equation for h, this would actually give us that h is equal to 300 times tangent of 75 degrees. Then, once again, we want to use a calculator because we don't know what tangent of 75 degrees is exactly, so we use that calculator to find the value. And we end up getting that h is going to be about 1,120 feet. So the height to the base of the cloud cover was approximately 1,120 feet. Normally when finding lengths of sides, we would round to 2 decimal places, but part of this question that did get cut off was round to the nearest whole number. So our nearest whole number would then be 1,120 feet. So our height was approximately 1,120 feet. So that was how we use our angle of elevation. So our theta that we were given, this was 75 degrees from the light detector, which was on the ground. And so we use our angle of elevation since our light detector is going to be detecting the light that hits the base of the cloud cover. So that's how we use our angle of elevation in this case. And luckily, we only had to find one value. We only had to find the opposite value. We didn't have to find anything else. Quite a bit of room there. Another application that we can use is what we call direction or bearing. So in navigation or surveying, the direction or bearing from a point O, I almost said 0, to a point P equals the acute angle theta between the ray of OP and the vertical line through O, the north-south line. So this sounds kind of confusing. If you are ever given a problem like this where you do not have an image to go along with it, it is very important to draw out your plane. But for our example, we are given a plane here with our different rays and lines that are drawn out. So example 5, from the figure below, what is the bearing from O to an object at P4? So let's read over our instructions one more time because it's a little confusing. So in navigation or surveying, the direction or bearing from a point O to a point P equals the acute angle theta that's between the ray of OP. So you have your point O and your point P, and there's a ray going through it. So your acute angle theta is going to be equal to that vertical line that goes through O. So, which in this case is our north-south line coming from our picture here. So once you have your picture, we're asking what is the bearing from O to an object at P4? All we have to do in our case is look for our point O and our point P4. So we have our point O and our point P4. We see we have our ray coming through here. And our bearing is just going to be this angle measurement. This is the angle measurement between our north and south line and our ray OP. So this is how you would read your bearing or a direction or a bearing question. You're just really seeing the angle between your vertical line and your ray that you've drawn out, which in our case is already given to us. So for our answer, we can just say that the acute angle between ray, in this case OP4, and the north-south line which goes through O. So a bit of confusing language there, but we're really just talking about that north-south line, or if you want to think about it in the XY plane, the y-axis. So the north-south line through O is 20 degrees. So it is 20 degrees, but it's helpful since we are giving direction, we do want to give directions as well. So these cardinal directions. So we know that it's going to be 20 degrees, but we want to give the cardinal directions as well. So north, east, south, west. So we can say the bearing from O to P4 is 20 degrees south, since we see that this whole area is south, and we're in the east part of our graph here. So if we wanted to label them, this would be the northeast part of our graph, this would be our northwest part of our graph, this would be our southwest part of our graph, and this is our southeast part of our graph. So when we write this out, we're going to label south first. So this is south 20 degrees to the east. So you label north or south first, your angle measurement of your acute angle, and then you list whether it's going to be east or west last. And that there would be our answer. So with direction and bearing, it is just a little bit confusing, but the actual concept of it is fairly simple. So all right, that finishes up our section 8.1 for today, and I'll see you again in section 8.2.